Welcome to Waidsum University. Today we're looking at chapter 8, implementing the virtual private networks. So today we want to look at the VPN, the virtual private network. But before we go into the VPN task and the VPN laboratory work, let's first of all look at the general overview of the VPN, okay? So without much ado, let's begin. First, we're going to look at the VPN terminology that are used in VPN, that we ensure that we're able to do the task and we're able to do the lab work. Okay, so this section will be divided into three. We have the VPN technology and theories, and then we have VPN task, and then we have the VPN laboratory work. Okay, so the first part is the first terminology we're looking at is the crypto system. In cybersecurity, the first part, when we're looking at VPN, we talk about the crypto system. What is a crypto system? A crypto system is a system that has been put in place to be able to carry out encryption mechanism, decryption mechanism, user authentication, hashing, and key exchange processes. So these are the keywords in crypto system. A system is said to be cryptographic if it's able to carry out encryption algorithm and decryption algorithm, and is able to do what we call the user authentication. There's an authentication, maybe using a preset key. We're going to talk about this. The hashing functions, the hash values, it's able to do that, and it's able to do the key exchange processes. So this type of system is regarded as a crypto system. And it's a suite of cryptographic algorithm that is needed to implement security services every time we have a network system or between networks, maybe from the head office of a big corporation to the branch offices. Okay, so we're going to talk about all of this. A crypto system may use one of the several different methods. Does it have to be just one method or one way? We're going to be describing the different methods that are used in crypto system, that support the crypto system. So it all depends on the policies that is needed for the various user traffic in any given situation that the user traffic finds itself. So you can see that in a crypto system, we always send a plain text, and this plain text will be encrypted. There is an algorithm called the encryption algorithm. Usually we go to choose the algorithm for encryption, maybe the DEA and the 3DEA and AES. So any of the algorithm that is used for encryption, we're going to select each of them. Then the key given by the DH, the DEFI HEPMAS functions. Okay, so the key that is also embedded in it, that is shared with the destination. Then this will put this in a ciphertext. So which means a ciphertext is an unintelligible logical message that cannot be read by any unauthorized users. So any unauthorized user can no longer understand this message. It becomes unintelligible for any authorized user, except you have the key to decrypt the message. So before we go to the decryption concept, and then before the decryption with the key, because the key has been shared with the receiver. So this receiver is able to use the key and the hash function to decrypt the message and get back the plaintext and receive the message. Okay, so this is the basics of crypto system. This is the basis of crypto system. But let's look more in depth. We started with the first one, which is the encryption, because when we mentioned the crypto system, we mentioned the encryption decryption concept. So we mentioned the encryption decryption concept as the first aspect or first preliminary phase of this cryptography. Now, the first one is the encryption and the decryption. Now, what does this encryption and decryption as a terminology that is used in cryptographic system? What does this encryption or decryption mean? Encryption is just actually a process, a way of transforming information, which we call the plaintext or the clear text, into a ciphertext. A ciphertext, like I said earlier, is a text that becomes unintelligible to anyone who do not have the cipher key, who do not have the encryption key. Okay, it becomes unintelligible to the person, and it's which is not readable by any authorized user. If you are not authorized, you don't have the key, you will not be able to understand the cipher the ciphertext. Okay, so that's encryption, putting a plain text or a clear text, a message, a normal message, into a form that becomes unintelligible by unauthorized people is what we call the encryption method. Encryption method. Now, the decryption is the opposite. Decryption is just the opposite. It's a way of transforming the ciphertext, that the unintelligible message that you put the message, back into the clear text message or the plain text message, making it readable by the authorized user, because the only one who can decrypt the message is the one who has the cipher key, who has the key, the decryption key, okay, who has shared the key with the original sender of the message. Okay, now let's take a look at the popular encryption algorithms that are used in the cybersecurity. Let's take a look at the three most popular encryption algorithms that are used in the cybersecurity. The first one is called the DES. Okay, not the DEA in US. Okay, this is DES, the Data Encryption Standard. The DES means Data Encryption Standard. It's an encryption algorithm that is commonly used in cybersecurity. Okay, to provide a crypto system. Okay, the second one is the triple DES. That's 3DES, which is a triple data encryption standard as well. Then the third one, the third algorithm that is used in encryption, is the AES, which is the Advanced Encryption Standard. Advanced Encryption Standard. So any of these three are commonly used in encryption in cyber cryptographic arrangement, okay, or in cyberspace. Now, another terminology that is commonly used with this cryptography or crypto system is the authentication slash hashing, authentication and hashing concept. Okay, you know, the hashing provides the authentication. Now, hashing or authentication, as it may, guarantees the message integrity. When a message is hashed, it guarantees integrity by using what we call the algorithm to convert the variable length of the message into a shared secret key. The variable length of the message and a shared secret key into a single fixed length string. So a variable length will be converted to just a single fixed length. Okay, a variable length will be converted into a single. So this is what hashing does, or authentication does, and with a shared secret key between the sender and the receiver, between the two people that have authenticated themselves. Okay, now popular hashing methods that we normally use for authentication are: one, the SHA. The SHA, we have SHA-1, SHA-2, SHA-5, SHA-7, SHA-256, and SHA-512. Okay, so we have what does SHA mean? SHA just means secure hash algorithm. This SHA simply means secure hash algorithm. Okay, this is the one Cisco uses. Okay, this is the one Cisco uses. Remember, we're doing Cisco cryptography. Okay, so this is one Cisco uses. And then the second one, the second popular hashing method, is the MD5. MD5 simply means Message Digest Method 5. Message Digest 5. Message Digest Method 5. Okay, so these are the two popular hashing technology that are used for authentication in a crypto system or in the cybersecurity space. Now, another terminology that is normally used in cybersecurity space is non-repudiation. Non-repudiation is the ability to prove a transaction occurred. The ability to prove, to show, like a proof, like a signature, like something to show that the transaction has taken place. It's just similar to a side packet received from a shipping company. You know, when you receive a packet from a shipping company, you have to sign so that he goes back to the office to show that the owner of the packet has actually received the packet, has taken the packet from him. So you have to sign before he can deliver the packet to you. So that's a non-repudiation. So the ability to prove that the transaction, something has taken place, okay? Now, this is very important in financial transactions and similar data transactions, right? So in the banking sector, in the financial sector, non-repudiation concept is highly important. It's very, very important. Another concept in cybersecurity or cryptographic study or crypto system is the Diffie-Hellman key exchange. This is very important, the Diffie-Hellman key exchange, okay? Because this algorithm generates the key that is being shared, okay? That is being shared between the the sender, the host A and host B, or the sender and the receiver. Okay, so how do the encrypted and decrypted devices get the shared secret key in cryptography? How do they get this shared secret key in cryptography? The easiest method is to use what we call the Diffie-Hellman public key exchange. The simplest method to generate and share the key, the secret key in system cryptography, is to use what we call the Diffie-Hellman public key exchange. Now, this Diffie-Hellman key exchange is used to create a secret key, a shared secret key without prior knowledge. Without prior knowledge, you will not be aware. Okay, you're not going to be informed. But when the negotiation starts, when the SA negotiation, IKE SA negotiation starts, we're going to talk about IKE SA negotiation later on. So when it starts, then the key will be generated by the DH. The key will be generated and will be shared between these two negotiating partners, okay, that are going into contracts. Now, this secret key is required by what? By the encryption algorithm, the DES, 3DES, and AES. So this key is needed by both the encryption algorithm and the authentication algorithm, or the hashing function, the hashing algorithm. So both the encryption and the hashing, they both need the secret key. And this key is generated by DH, the Diffie-Hellman key exchange method. Now, the pre-shared key. Now, this key, what is it for? Why do we need the key? This key, it identifies a communicating party during a phase 1 IKE negotiation. IKE is simply Internet Key Exchange, okay? IKE is Internet Key Exchange. It has two phases of negotiation. During the phase 1, it will negotiate for the IKE associations, SA, the security association. It will negotiate for the security association between two hosts, between two people that wants to embark on whatever transaction on the internet or whatever data packet they want to share. They have to negotiate and they have to understand each other and they have to protect each other using the crypto system and the cryptographic key system exchange generated by the DH, the Diffie-Hellman algorithm. Okay, now this key must be pre-shared with another party before the pairs routers can communicate. If you don't, then there will be no security. All we're talking about will be in vain. So this key has to be pre-shared with one another, with the parties, the host A and host B, before the routers can communicate. Or else the router will not feel there is a security in place in order for it to communicate or to transfer packets from one place to another. Now the next one is the IPsec. IPsec simply means Internet Protocol. IP means Internet Protocol. Internet Protocol Security. That's what we mean by IPsec. IPsec is actually a framework. It's whole. It's like a whole. It's putting everything we've talked about into a concept, into a perspective. Okay, we're going to show it with a block diagram. The IPsec is a whole concept. It's a framework of open standard. This framework is developed by what? By the Internet Engineering Task Force. Okay, so it's a regulatory body that determines the security architecture and the security protocols and the securities on the internet. So this framework was developed by the Internet Engineering Task Force to create a secure tunnel, because the whole essence of IPsec is to create a tunnel, a secure tunnel, because this is the whole essence of the VPN. This is the whole essence of a VPN in a network. This is the whole essence of a VPN, the virtual private network. This is the whole essence of using a VPN, to create a tunnel, a secure tunnel between one office and another office, between one user and another user, between a user in a headquarter or head office and a user in a branch office. So the whole thing is a virtual private network. Is just to create a tunnel in a public infrastructure. It takes your data through the public infrastructure that ordinarily you didn't want it to. You want a private system, a private security. But you know what? You don't have to worry, because this system is going to create a tunnel upon which only its data and packets go to go through, and these data and packets will be protected in the public infrastructure environment. So it's not going to be like left alone and let your data to be tampered with on the public space, on the internet space. So the data will be protected. Why? Because a tunnel has been created for the data alone that have created this association, this SA association, the IKE association, to go through only. Okay? So we don't have to worry. So IPsec is a framework of standard developed by IETF, like we stated, Internet Engineering Task Force, to create a secure tunnel at the network IP level. At the network IP level. And it spells out the rules for this secure communication. It gives the guide, the rules. Okay? Now, IPsec is not bound to any specific encryption or authentication or decryption or hashing or key technology or hash technology or security algorithm. It's not bound to anyone. It can update. It can get new ones, better versions. It's not like super bound to any specific one. It can use all of them put in place. Okay, now let's take a look at the framework, the IPsec protocol framework, like we said in a block diagram. Okay, now in this engineering of IPsec, we will look at the whole framework. The first is the IPsec protocol. Okay, the first is the IPsec protocol. What protocols are used in this tunnel? What protocols are used? Is one of the protocol is the ESP protocol. And ESP simply means encapsulated security payload. Encapsulated security payload is one of the protocols that is being used. There are two protocols that are used in the tunnel. One is the ESP, the other one is AH. AH is authentication header. AH is authentication header. But they are put in three different categories. One, the ESP can be used alone as a protocol. The ESP can be used alongside with AH as a protocol, or AH can be used alone. So there are three categories, despite we only have two types of protocols that are used in the ESP framework environment. Okay, so that's the first one, the protocol, the IPsec protocol. The second one is the encryption. The encryption we already mentioned. In the whole framework, IPsec framework, the encryptions that are available, the choices that you have, that you can choose from, is the DES, the data encryption standard, the triple data encryption standard, and the advanced encryption standard. So you can choose any of these. Any of these can be used, okay? These are for the framework. Okay, the next one is the authentication. Remember we said IPsec protocol, the encryption, the authentication, and the DH. Okay, the authentication is the hashing function and hashing methodology. Okay, we either use the MD5 or we use the SHA. Remember, secure hash function algorithm. That's the SHA. But this is Cisco compliance. The SHA is the Cisco compliance. So it's always preferable. Cisco is by default. Cisco use the SHA method. Okay. Then the fourth part of the framework, or fourth concept of the framework, is the DH, the Diffie-Hellman key generator. The Diffie-Hellman key generator. So we have the DH1, the DH2, the DH3. Remember, this key has to be inscribed into the encryption and the authentication. The key has to be given to these two concepts, and the protocol also has to be given. In order, all these four has to go through the tunnel. All these four goes through the tunnel when we are talking about the VPN. We're going to talk about the VPN in a short while. Okay? Now, crypto map. Another terminology that is used in cryptography or cybersecurity is the crypto map. Now, a Cisco iOS software configuration entity that performs two primary functions. Now, this function defines what a crypto map is. This function defines what a crypto map is. The first is that a crypto map selects data flow that needs security processes. The map will select the data flow that needs what? Security processes. The second is that it will select it, or it will define the policies that this whole system is going to use. It will define the policy for this flow and the crypto pair that traffic needs to go to. Or the pair that the traffic will flow through, it will define the policies for it. So two things a crypto map does is a software a Cisco iOS software that performs these functions, that selects the data flow that needs security processing and define policies for this standard. Okay, so a crypto mark is applied to an interface. It's usually applied to the interface. Okay, usually when you're configuring, you apply the crypto mark to the interface to enable this functionality that we've described. Another terminology that is used in cryptography or cybersecurity or crypto system is the security association, which we call, or which we normally for short call the SA negotiations, the security associations. Now, a security association is simply like a contract between parties, two parties, indicating what security parameters they're going to be sharing with each other. So, two parties, a contract between two parties that we define the security parameters that they will be sharing. It could include the keys, the key, what key they will share, the key they will share, the DH keys, the pre-shared key they will share, the algorithm they're going to be using, the authentication method, whatever, all of this that we've described, that they're going to be using. So this contract arrangement between the two parties in a network environment is called the security association. It's called the security association, SA. And a security parameter index, SPI, identify each established SA. So there is what we call security parameter index that identify the established SAs. It will show, SA has been established between these two hosts or two parties. Okay. Another terminology used are the cryptographic names. Usually we use Alice and Bob's. Okay. Alice are commonly used placeholders in cryptography. Okay. And then they're better than using the PCA and PCB. In cryptography, we use Alice and Bob. And generally, Alice wants to send a message. Usually the one that wants to send a message to Bob. Sometimes also we use Carol and Charlie. If we don't use Alice and Bob, we use Carol and Charlie. Carol and Charlie is Carol or Charlie. It is a third participant in the communication. Okay, it doesn't mean they will replace Alice and Bob. Actually, it's actually a third party in the communication eclosion or communication environment. Then also we use the fourth party participant, Dave. Dave is also used. So the thing goes on alphabetically. They choose name. Then we use Eve. Eve is eavesdroppers. Someone listening to hear like an attacker is Eve. So Mallory or Mavi or Mallet is used as a malicious attacker. Okay, the attacker now is Mallory or Mavi or Mallet. Okay, so he or she will try to modify and substitute the messages, replace them, or the old message, or do a denial of service. It's just an attacker, a malicious attacker that is more difficult to monitor. That's the name we use for them. Then water. Water is rewarding to guide Alice and Bob depending on the protocol that they use. So these are the names that I use. Now let's go to the VPN proper. VPN. We have a conventional private network. In a conventional private network, we always use what we call the frame relay. Okay, this one does not go through the public space. The public space, like the internet, is different. The central or the head office have its own dedicated system. So to send something to his branch office, and using a frame relay, and what we call, they have to set up frame relay service. Okay, so this goes through a frame relay service to from one office to another without going through the normal public internet. So this is what we call the conventional private network, and this is super expensive. It's very costly, so it's very costly. It's going to cost your business a lot. So that's what leads to the VPN, the development of the VPN. So here it has higher cost, it's not very flexible, it's less flexible. It involves a lot of that's wide area network management, so many things. It has complex topology, so it's not so friendly. Okay, the second one is the virtual private networks, the one we'll be describing. It's easier, it's cheaper, it's more flexible, simpler management, topology uses the tunnel, and this is the tunnel as it were. Okay, it uses the tunnel. Let's highlight the tunnel. It uses the tunnel. It's over the public infrastructure. Over there, the internet is a public infrastructure. So you create a tunnel. This is a head office. It's going to go through the internet, but through a tunnel. So it's not like it's open. Your data are open to the public in the internet. No, your data are going to go through a tunnel and to your branch office. So this is what we call the VPN, the virtual private network tunnel. Okay, so this is different. You see, you're not going to use a relay service anymore. You just create a VPN, a virtual private network. Okay, now VPNs, a virtual private networks provides the same network connectivity for remote user over a public infrastructure, as we've explained already. The same network connectivity over a public infrastructure as they would have over a private network. So just as it will have, if you have gone through the relay service or frame relay method. So it's going to give you the same thing, but cheaper for you and more easy to control and manage. So that's a VPN. A VPN provides a network connectivity for remote users over public infrastructure and has an advantage as if you are private. You pass it through the public space, but you are privately passing through the public space. That's the concept of a VPN. VPN services for network connectivity includes the authentication. That's authorized users only. No one, if you're not authorized, you cannot pass through this tunnel. Only the authorized users can pass through this tunnel. So for VPN, only the authorized user from the central office to the head office to the branch office. The rest of the public people in the internet cannot access what is going on. So VPN is for authentication. It supports authentication. The connectivity, network connectivity supports authentication, meaning only authorized users will have access to the exchange or the data exchange or whatever, or the packets. Then another advantage of what the VPN provides is data integrity. It's such so that no one can tamper or alter the data that is passing through the public infrastructure because it's passing through a tunnel. It's not just passing through a public space. A tunnel has been created for it to pass through. Then it also gives a very unique confidentiality, meaning no one can eavesdrop. No one can eavesdrop. No attacker can begin to eavesdrop to copy your message or your packet and make other use of it. So you can see the characteristics of the VPN as itemized. This is one office, could be head office. Okay, this could be a head office, and let's say this is a branch office, for example. This is a branch office, but over here we have the internet, and then you can see we have a tunnel. So this tunnel is the VPN. We've created a tunnel to take our data to pass through the public internet infrastructure to another place. So when we do this, then we've created a VPN. This is what we call a VPN instead of using a frame relay in a privacy sector system. Is that okay? So let's move on. Now, VPN concept. A secure VPN is a combination of concepts, meaning a virtual network to tunneling. So all your network goes into a tunnel. That's the meaning. From your router gateway, everything enters into a tunnel. Like a tunnel, normal tunnel. You go into a tunnel, and then till you come out on the other side to the office. So virtual network to a tunnel, and then private network to encryption. So it's going to, meaning VPN will be combining tunneling plus encryption. You have to encrypt, even if you are going through a tunnel, you have to encrypt the data and still protect the data and still provide all the cybersecurity mechanism to protect the data. So which means a virtual private network is equal to tunneling plus encryption, because virtual network is tunneling. When you say virtual network, means to create a tunnel. It means to create a tunnel. When you say virtual network, it's to create a tunnel. When you say a private network, is to create what? Encryption. Is to encrypt the data. When you say private, it's to create encryption. So when you put it together, virtual private network when you put it together, virtual private network is equal to the tunnel plus encrypted message or encrypted data. Is that okay? So let's move on. Now the VPN packet encapsulations. The encapsulation of the packet, what goes with the packet. Okay. First, we have the carrier protocol. The protocol over which the information is traveling. Your frame relay protocol, your ATMs, your MPN. So that's one. The encapsulated protocol, which is the protocol that is wrapped around the original data that goes into the tunnel. There are two main protocols or two very serious protocols we're going to describe in this course, which is the GROE, okay, and the IPsec protocols. These two protocols, they are wrapped around the data packet that is going through the tunnel, and they take it through the tunnel till it gets to the end. But they're not only limited to these two. We have the L2F protocol, PPTF protocol, N2TP protocols. Then the next one is the passenger protocol. The passenger protocol is the protocol over which the original data was being carried, the original data, before we now wrap the cryptographic concept upon it. So the original data goes with the protocol IPS, AppleTalk, IP version 4, IP version 6. These are the original protocol the data is coming with. Okay, and it's called the passenger protocol. So there are three categories of protocols. The carrier protocol, like the relay, the frame relay, ATMs, MPLS. The encapsulated protocols, which are encapsulated protocol is the one we'll be concerned with in this course, the GROE and the IPsec. And then the passenger protocol, which includes the original protocol the data was coming with. Okay, so here we have the sender. This is a telephone line. Okay, and then these are the protocols, available packet from the client's computer. The original packet protocols, IP protocol, PPP, TCP, and SMP. So it goes into this ISP, Internet Service Provider, okay, and then the Internet Service Provider, they have a route to the VPN device connected to access server, and this VPN device now send it to a tunnel over the public Internet. Goes through a tunnel. Before it goes through a tunnel, there are so many things that will be applied to it, so many packets in transmission protocol, like the GRE we've mentioned, the L2TP, the PPP, and so on and so forth. All this will be applied to it to go through the tunnel. And as it goes to the tunnel, it will reach the receiver side. On getting to the receiver side, the data will be extracted, will be decrypted, and this is called the VPN tunnel. This one is the tunnel, VPN tunnel, over the public Internet or public infrastructure. So when it's received here, the VPN device will decrypt it. The VPN device will decrypt it. Remember, the VPN device will encrypt it over here, and they'll get it here. The VPN device will decrypt it, and then it will be accessed by the server, and then the receiver will receive it. So this is the concept. This is just the frame concept. Now let's take a look at the VPN topologies. There are two types of VPNs. One is called the site-to-site. One is called the site-to-site VPN, which is used by large corporations. This site-to-site segmented into two. We have the Intranet VPN, which connect corporate headquarters, remote offices, and branch offices over a public infrastructure. Okay, the Intranet, the Intranet VPN connects your head office, your remote offices, branch office over a public infrastructure. Then the extranet, that's for the Intranet. The extranet VPN links the customers, the supplier, the partners, and the communities of interest to a corporate intranet over the public infrastructure as well. Because everything has to go through the public infrastructure. That's what makes it a VPN, okay, a tunnel in a public infrastructure. Now, the next one is the remote access VPN. The second one, apart from site-to-site VPN, we have the second one, remote access VPN. Remote access VPN securely connects remote users, such as those using the mobile phones, the mobile user, and telecommuters to the enterprise, to the big enterprise. Okay, so meaning you just add a similar, but this is for site to site. Okay, from this business partner to this regional office. Okay, a tunnel will be created over this public internet. A tunnel will be created. Let's assume this is a tunnel. Tunnel will be created here. Here to here, a tunnel will be created, and so on and so forth. Okay, so this is the side-to-side VPN, just creating a tunnel from between the branches, office, end office, and all of them with the same organization, within the same organization. Then that's called the e-channel. The side-to-side, you can see the side-to-side VPN. You see from this is the remote office. So everything is set. All these are the users. Then it goes through this, and the VPN router. We prepare the data to go through the tunnel by including the IPsec transform. Okay, IPsec transform, the GRE. We'll talk about the transform to go through the tunnel to this main office. Also, from this remote office can send to another remote office using this tunnel and over the internet. And this remote office can send through the VPN route also to the head office. So this is the concept of site-to-site VPN. This is the concept of site-to-site VPN. Okay, let's take a look at the remote access VPN. It's just to have someone like your partner, customers from their house send it through the internet to the main office or to the regional office and so on and so forth. So that's called the remote access VPN. Yeah, someone uses a mobile phone but accessing the network, sending message. It's a partner, it's a known partner, not a fraudster or a hacker. Okay, so that's called the remote access VPN. Okay, now let's take a look at remote access VPN. You have to have username and so on and so forth. Okay, now let's take a look at the Cisco VPN product line, the product choice and the remote access or site-to-site. Now, for example, if you choose a product like Cisco VPN enabled router, which one is primary role is the site-to-site. Secondary role is the remote access. Then if you choose a product like Cisco PX500 series security appliance, the first one is site-to-site VPN, and the secondary one is the secondary role. Okay, the remote is the secondary role. If you choose Cisco ASA 500 adaptive security appliance, then it changes now. The remote will be the primary role and the site-to-site will be the secondary role. If you choose product like Cisco VPN 3000 series concentrator, then the remote access VPN will be the primary role and the secondary role will be the site-to-site. If you choose product like home router, leak systems, D-Leaks, the remote access will be the primary role and the site-to-site will be the secondary role. Okay. Now let's go to the GRE tunnels. Now the tunnels, this GRE is a protocol, right? GRE and IPsec, they are protocols that help the data packets to go through the tunnel. Okay. Now let's take layer 3 tunneling. There are two popular site-to-site tunneling protocols that are usually used. The first one is called the Cisco GRE, which is generic routing encapsulation. Okay, this GRE simply represents generic routing encapsulation. And the second protocol that is used in site-to-site tunneling protocol is the IPsec, IP security protocol, called the IPsec. Now, when should you use the GRE and or the IPsec? Let's find out. If you have a user traffic and you are considering the IP only, if it's only the IP only, and you also want to use a unicast only, then IPsec is VPN is desirable, most desirable for you. It's most desirable for you. So you are considering your user traffic and you use the IP only, and you're also looking at a unicast only, then IPsec VPN is most desirable for you. But if you are not considering only IP, you are considering other things, then you use the GRE tunnel. Use the GRE tunnel. Also, if you are not considering only unicast, it's more than unicast, you have multicast, broadcast, then it's better to use the GRE tunnel. However, these two protocols can be combined. The GRE protocol and the IPsec protocols can be combined to pass through, take the data packet through the tunnel. Can be combined to take the data packet to pass through the tunnel. Okay? Now, generative routing encapsulation, GRE. GRE can encapsulate almost any other type of packet, can encapsulate it. It uses the IP to create a virtual point-to-point link between Cisco routers. and it supports multi-protocols, IP, CL, CLNS, and IP multicast tunneling, and therefore routing protocol. So it can support multicast, not only unicast. So when what you are going to pass through the tunnel is more than, because unicast is only for IPsec protocol. If it involves multicast, then you have to use the GRE protocol. Best suited for site-to-site actually. Okay, the GRE is better for site-to-site multi-protocol VPNs. Okay, now let's take a look at the normal data header contains the IP, TCP, and the data. This is the normal header. Okay, normal data. Then you must add a carrier like the GRE protocol. So when you add this GRE protocol, this is the original IP packet. This is the original IP packet, IP, TCP, and data. This is the additional. Okay, to enable the packet to be able to pass through the tunnel, you have to add the GRE IP. Okay, now the GRE itself is divided to flags and protocol type. Okay, it's divided to flags and protocol type. Default GRE header. This is the GRE header. This is the data header, the original data. This is the header. So this is the GRE header, flags and protocol type. Now the flags, what does it do? It identifies the presence of optional header fields. Optional header. If you need any optional header, the flags can identify it for you. The protocol type identifies the types of payloads. Either the OX800 is used for IP. So the type of payload that this GRE is going to use, or this data packet is going to use. Okay? Okay, now optional GRE extension. Now GRE can optionally contain any one or more of these fields. These are options, okay? These are options. The tunnel checksum, the tunnel key, the tunnel packet sequence number. These are optional things that GRE can contain. Meaning, you know, just now we were only looking at the flags and the protocol type. So we can extend it and add all these options. The checksum, the number, the tunnel number, sequence number, the tunnel key. So which means our GRE, we can have the flag and the protocol type, which we described already. These are additional or optional extensions that can go with the header, the GRE header. The checksum, the offset, the key, and the sequence number. Okay? Now the key, what is the key? What's the purpose of the key? The key is used for basic playtest authentication and to distinguish between tunnels using the same source and destination addresses. Okay? And then for especially if you have parallel tunnels. If you have parallel tunnels, so to be able to determine which tunnel is this one is supposed to go through. And then the sequence number keeps the track of the packet order. Keeps the track of the order of the packets. Okay? Now, generic routing encapsulation, still on GRE, does not provide encryption. Okay, this is why I always advise we combine the IPsec and the GRE. Because although GRE is very good, but it does not provide encryption. But IPsec can provide encryption. So combining them will be a very good option. However, GRE and IPsec can be used together. You see, can combine, they can be used together. IPsec does not support multicast. We already established this. IPsec does not support multicast. It only supports unicast. Unicast does not support multicast and it does not support broadcast. And therefore does not forward the routing protocol packets. It does it because it does not do broadcast. So, however, IPsec can encapsulate GRE. So the IPsec itself can encapsulate a GRE packet that encapsulates routing traffic. So, which means we can call it GRE over IPsec. In this case, like I said, always combine them. In this case, it provides you that flexibility and optimal advantage. Okay. Now let's take a look at the 5 steps to configuring a GRE tunnel. 5 steps to configuring a GRE tunnel. First of all, we have to create the tunnel interface. Anytime we are doing a configuration, remember we have to create the interface first. So we say in the global configuration mode, we create the interface tunnel 0, right? Then we assign the tunnel an IP address. And then we define the source tunnel interface, the tunnel source. And then we identify the tunnel destination. We create it. And then we identify the protocol to encapsulate in the GRP. Which protocol we go to encapsulate in the GRE tunnel? So we type tunnel mode GRE IP. So you already say you are using GRE. Okay, by default, GRE is a tunnel in IP packets. So it's already by default in every IP packet. Okay, by default. So this is the 5 steps to configure GRE tunnel. Look at it. We already give them. You create the interface. You say router 1 config hashtag interface tunnel 0. Then you put the IP address router 1 config interface hashtag IP address 10.10.1.1. Then you put the subnet mask 255.255.255.252. Put the subnet mask. Okay, you follow it with the subnet. This one. Okay. So you're configuring the router interface. And then you put the tunnel source serial number, the serial. This serial 0/0. So you put the tunnel serial number, and then you put the tunnel destination address. The destination address is 209.165.200.225. You put the destination. This is the destination for this router. This is the source. This is the destination. So you put the destination address where it's going to go. The tunnel mode GRE IP, you type it. The same you do for router 2. But it's just that when you are doing for router 2, you put the destination as router 1. Put the destination as router 1. Is that okay? So tunnel GRP example. Here is the example. Here is just to check what you've done. This is the tunnel to pass through the public internet. Okay, this is branch A, branch central A, the head office probably. So you say branch A after show running config interface. So what we just did just now, you show it running config, it will display all this one that you have configured. Okay. Okay, now let's go to IPsec. We've talked about the GRE, which is one of the protocols that is used in the tunnel. Now let's talk about the IPsec, which is the second protocol that is used in the tunnel. The IPsec is Internet Protocol Security. We also is a framework of standard developed by we already established this, by the IETF to create a secure tunnel at the network layer, IP layer. It spells out the rule for the secure communication. Okay, IPsec is not bound by any specific encryption or authentication. We already established all this. So IPsec framework, we already talked about this. It guarantees the IP security. In the framework, you have the IPsec protocol, confidentiality, integrity, authentication, and DEFI. So let's go through them one after the other. What are the protocols that we use for the IPsec? We have AH protocol, ESP encapsulation. We have the ESP, and then we have the combination of both the ESP and AH as a protocol combined. Then for the confidentiality, we use the DES, 3DES, AES, and SEAL. Then for integrity, we use the hash function to provide integrity. We use the MD5 and SHA, secure hash algorithm. That's SHA. Then authentication, we use the PSK and RSA. The DEFI to generate the key. We use the DH1, DH2, DH5, and DH7. Okay, so the IPsec protocol framework, looking at the framework, the protocol framework, you can see the IPsec, we have the first one is the IP protocol, which we already described, IPsec protocol. Then the next one is the confidentiality. In the confidentiality, we say the least secured method to use for encryption is the DES, and followed by a secure one is 3DES. A very secure one is the AES, and the most secure one is SEAL. Okay, the DES supports a key length of 56 bits. 3DES supports 56 bits, and thrice of it. The key length, thrice of the 56 bits, and the AES key length supports 128 bits, 192 bits, and 256 bits. And the SEAL supports about 160 bits key length. For integrity, the most secured one is the SHA. You use the SHA and the MD5, but the most secure one is the SHA. The MD5 key length is 128 bits, and the SHA key length is about 160 bits. So for authentication, it uses the PSK and RSA. And for the FIHEMA, it uses D1, D2, DH1, DH2, DH5, DH7. And each one has its own bit. So DH1 supports 768 bits, DH2 supports 1024 bits, DH5 supports 1536 bits, and DH7 supports even a higher number. Now, DH1 and DH2, they are used by DES and 3DES, while DH2 and DH5, they are used by AES, okay? IPsec framework protocols. IPsec uses two main protocols to create security framework, the AH and the ESP. IPsec uses two protocols to create the security framework. One is the AH, the authentication header, and the encapsulated security payload. Okay, so authentication header, AH provides authentication as the name sounds, provides authentication and optional replay detection service. And how does it do this? It authenticates the sender of the data. AH also operates on protocol number 51, and ESP operates on protocol number 50. AH supports the HMAX MD5 and HMAX SHA-1 algorithm. Okay, so all data in place, as you can see the router. So it supports, these are what the header gives, this AH algorithm, protocol, what it gives. Okay, now authentication header, still on the authentication, AH does not provide confidentiality. It does not provide encryption, so we need ESP. Okay, so it's appropriate to use when confidentiality is not required or permitted. So whatever it's transmitting is going to be unencrypted. So it's better to use the ESP, right? Or we combine them. It only ensures the origin of the data and verifies that the data has not been modified during the transit stage. And if the AH protocol is used alone, it provides weak protection. So you have to use it with ESP. That's why we prefer AH plus ESP protocol to be used. AH can have problems if the environment uses NAT. Okay, encapsulated security payloads. This is the second one. And ESP provides same security services such as the one the AH does, like authentication integrity, and plus encryption. So this is why ESP now is very good to use. It provides the same as AH, authentication integrity, and additional features that it has, that it provides that AH does not have, is the encryption service. The ESP provides encryption alongside with authentication integrity. So it can encapsulate the data to be protected, and it operates on the protocol number 50. We established that already. Okay? So it provides encryption. So you can see there's encryption mechanism in this for the confidentiality part, encryption. Here, AH does not have the encryption part. You can look. AH does not have the encryption. Encryption is missing. Confidentiality part is missing. So AH does not have the encryption part. These are the only choices you have. Integrity, authentication, and the FIHEMA. But ESP has integrity, authentication, confidentiality, and the FIHEMA. So it provides the confidentiality, which is this is the encryption part. This is the additional feature it has that AH does not have. This one is the additional option, encryption, that it has that AH does not have. That option is wonderful. Okay, don't feel, oh, it's only this. It's wonderful because your data needs to be encrypted before it can pass. Even if it's passing through a tunnel, it needs to be encrypted. Encapsulated security payload is still on the ESP. ESP can also provide integrity authentication. We already mentioned this. Now, first, the payload is encrypted using the DES by default, or 3DES, or AES, or C. Next, the encrypted payload is hashed to provide the authentication and data integrity using the HMAC MD5 or HMAC SHA-1. So the hashing function or the authentication is provided by the hashing functionality. Okay, so ESP is super good. So first of all, this is the original, this is the encrypted face of the original data. IP header, data, ESP trailer. See, encrypted. Then when you include ESP header to this original encryption, it becomes authenticated. Okay, this one is for transport mode. This one is for transport mode. Okay, we're going to talk about that. Original data just has this. It doesn't have the ESP trailer. Okay. Transport mode and tunnel mode. Now we're going to look at these three phases. We have the original data, the IP header, and the data itself only. That's what the original data has, original packets. Then the transport mode now added, apart from data and the IP header, see this is the IP header, the transport mode added ESP header, ESP trailer, and ESP authentication. So has been added to the transport mode. However, the best mode, which is the tunnel mode, now add a new IP header, and a new IP header to it, right? So it now has a new IP header to what we have, and also ESP header, although this one already has ESP header. So you can see the authentication is here, and this one has a new IP header. This makes it very unique. Now let's take a look at the differences between the transport mode and the tunnel mode. Security is provided only for the transport layer and above. Only the transport layer and above. Below it, no security. So it protects the payload but leaves the original IP address in a plaintext. It protects the payloads but leaves the original IP address in a plaintext. This makes it vulnerable. So ESP transport mode is used between hosts. It's just used between hosts. The transport mode works well with GRE because GRE hides the addresses of the end devices by adding its own IP header. Okay, so this is the transport mode like we looked at. Now let's take a look at the tunnel mode. So the tunnel mode provides security for the complete original IP packet, the whole packet. The tunnel mode will provide security for it. Okay, so the ESP tunnel mode is used in remote access and site-to-site. So you can use it for either, we're going to talk about types of VPN, the remote or the VPN topology. There are two topologies for VPN. I think we mentioned it. Remote access topology and site-to-site topology. There are two topologies using VPN. Okay, so it provides a whole security for the whole packet. Now let's talk about the key exchange. Key exchange, the IPsec VPN solution. The IPsec VPN solution, okay? Now negotiate the key exchange parameter called the IK, Internet Key Exchange. The IPsec VPN solution will help to negotiate the key parameters. Establish a shared key, that's by DeFi-HEMA. Authenticate their peers by using a hash function. Negotiate the encryption parameters. Okay. Now the negotiated parameters between two devices is what is known as the security association. The negotiated parameters between two devices is what is called the security association. Now let's define security association properly. Security associations represent a policy contract between two peers or hosts and describe how the peers will use the IPsec security services to protect network traffic. SAs contain all the security parameters needed to securely transport packets between the pairs or between hosts and practically define the security policies using the IPsec. Okay, so SA parameters. Okay, this is host 1. These are the security details it has. It has generated the encryption, the hash, the key, the lifetime, so everything is negotiated. So it's going to tell the B, this one, and this one will also tell what it has. Then they will establish a connection between themselves. Okay. So IK simply means Internet Key Exchange, right? It's also interchangeably used for ISAKMP. They use it interchangeably. Okay, they are used interchangeably. IKE helps the IPsec securely exchange cryptographic keys between distant devices. So, what the IKE, the job it does is to help the IPsec to secure exchange of cryptographic key, okay, between the devices, distant devices that are not even in the same place. See, so one thing is the combination of the ISKM, ISAKMP, and the Oakley key exchange protocol. When they combine, they form this IKE. Key management can be pre-configured with IKE or with the manual key configuration. Anyway, whether we say IKE or ISKMP, they use interchangeably. We are saying the same thing. So the IKE tunnel protects the SA negotiation. The IKE tunnel protects the SA negotiation. And after the SAs are in place, the IPsec protects the data that Alice and Bob will exchange over the Internet. Now let's take a look at the flow concept. The first thing to do is the Alice router. Alice outbound packet is sent from Alice to Bob. Here is Bob. It's sent from Alice to Bob, no IPsec SA. So we just send the outbound packets to Bob. Okay. Then the second thing is the Alice IKE begins negotiation with Bob's IKE. The IKE of Alice from the IPsec in the just into the tunnel begins to negotiate with the Bob's IKE. The third process is the negotiation is complete. Once the negotiation is complete, Alice and Bob now have a complete set of SA in place. They've negotiated with themselves and they've recognized themselves. So they go to send through this tunnel and receive. The fourth one is the packet is sent from the Alice to Bob, protected by SA, IPsec SA, because they've negotiated and they've understood themselves. Now, still on the IKE, there are two phases in every IKE negotiation. The phase one is the authentication phase. Phase two is the key exchange, exchanging the key. Now, let's talk about them one after the other. The IKE negotiation also occur in the main mode and the aggressive mode. The main mode has 6 messages, exchanges 6 messages, or require the exchange of 6 messages, while the aggressive mode requires only the exchange of 3 messages. Now, IKE phase 1, when we look at the main mode, phase 1, negotiates an IKE protection suite, exchanges key materials to protect the IKE sections, that's the DH, authenticate each other, establish the IKE SA. We mentioned all of this in a way. Okay, now let's move on. So let's just take a look at what is going on. This is IKE phase, especially phases. Okay, this phase 1 and this phase 2. Okay, phase 1 is the aggressive mode exchange. IKE phase 1, aggressive mode exchange. So these are the security policies this one has. Sender IKE policies set an ROA DH key. It tells it I have policy 10, DEA encryption, MD5, pre-share, DH1, and lifetime. So this is the key. It sends to the other guy. This one says, okay, may I have this policy 15, DES, MD5, pre-share, DH1. This one sends his own key back to this one. Now they will confirm IKE policy set, calculate, see, to confirm IKE policy set and calculate the share secret and send router to the HQ. So once they see the security set are in place, then router 1 will send router 2 the DH key. Okay, then router 2 will do the same. Router 2 will calculate share security, verify the peer identity and confirm with peer. And then authenticate peer and begins phase 2. This is the exchange, the IKE phase 1 exchange. Once this happens, they will start phase 2. Phase 2 is IKE phase of phase 1 is to generate a connection, negotiation. Phase 2 is to exchange the key. or what we call the IPsec policy. So they both negotiate the policy, IPsec policies. Okay. Step one, host A. Look at the host A. Here's host A. Host A sends interested traffic destined for host B. It sends an interested traffic destined for host B. Step two, we say the IKE, that is Internet Key Exchange, phase one, authenticate IPsec peers and negotiate the IPsec essays. First of all, authenticate the IPsec peers, the two, and then negotiate the IKE essays, that's security associations, to create a secured communication channel for negotiating IPsec essays in phase two. Okay, so IKSA, IKE phase one, and then IKSA. Then step three, IKE phase two, negotiate the IPsec SA parameters and create matching IPsec essays in the peers to protect the data and the message exchange between the endpoints or between the two PSs. Step five, data transfer occur between the IPsec pairs based on the IPsec parameters and the key stored in the SA database. Then step five is to do termination. IPsec tunnel termination will now take place after all of this has been done. Okay, so interested traffic, if you send, host A send through this data, if it's an interested traffic, yes, then IPsec will apply. If not, send back the clear test. So step two, IK phase one. So what this router has, the security policy, IKE policy 10, DES, that's my encryption, this is my hash, pre-shared value, my authentication, DH1, this is my key and lifetime. And then this one exchange, they exchange their IKE policy set, they exchange, okay? Negotiation matching, IKE transform sets to protect IKE exchange. If they match, they will transform this policy to they will transform this into policy sets. Okay. Now, IKE phase one, the DH key exchange. See, router one randomly chooses a string and send it to router B. This router one sends a string, randomly sends a string to router B, and then router B hashes the received string together with the pre-shared secret and yield a hash function. Then what happens is that router B now sends the result of the hash back to router A. Now, if router A calculates its own hash of the random string together with the preset secret and it matches with the received one from the other pairs from router B, if they match, then router B knows that the pre-shared secret and is considered authentic or is considered authenticated. So they can begin the exchange. DHK exchange, we say route to, when you, this policy set now, router B randomly chooses a different random string and send to router A. Okay, the first stage was router A send it to B. Now B send a different string and send to A, and A also hashes the received string together with the preset secret and yield a hash function, and then router A, after that, we send the result of the hash back to B, and router B will calculate the sole hash of the random string, calculate together with the preset secret, and matches it with the received result from the other pairs. If they match, then A knows that the preset secret is considered authentic. So this is what is going on before exchange. Peer authentication. This is the remote office, this is the corporate office. So a tunnel is going to be passing through this Ethernet. Okay, peer authentication method. What the things you need for authentication is your pre-shared keys, RSA signature, and RSA encryption verses. Okay, phase two, what you need is the IPsec negotiations. Now, negotiate IPsec security parameters or transform stuff. So you negotiate IPsec security parameter and IPsec transform sets. And then you establish IPsec essays and periodically negotiate the IPsec essays to ensure that there's security constantly and also perform an additional DFMI exchange. So this is phase 2, what you're supposed to do in phase 2. What this negotiation is all about, IPsec security parameter negotiation. So you can see transform, we call it transform set negotiation. So here they negotiate the whole set, what they have. Okay, a transform set is a combination of the algorithm and protocols that enact a security policies for traffic. So here we're going to negotiate both the algorithms and the protocols that define this security architecture. Okay, and this is done in phase 2. Okay, so you negotiate, you can see they're negotiating. This is what I have, negotiating, this one is negotiating with this. Okay, so IPsec session, you can see the IPsec section is a tunnel where the essays are exchanged between peers. These are the peers. Essays are exchanged between peers, security associations. The negotiated security services are applied to the traffic to go through the tunnel. After that is done, we terminate. Termination occurs, tunnel is terminated when the essay lifetime has expired, has timed out, or the packet counter is exceeded, or the IPsec essay is removed. The termination will happen. Tunnel will be terminated. Okay? So we stop in this first part here. Our second part will be looking at the IPsec task force, the task that is being done. Okay, thank you for joining us today.